So, V b is equal to V c equal to I b plus I c into Z f is equal to 3 Z f I a 0. So, in this case your what you call that this one we will come to that, this one why we are writing 3 Z f I a 0. So, here if you see we will see that I b plus I c is equal to 3 I a 0. I am making it here on the right hand side here. I a 1, I a 2, I a 0, you know 1/3, 1 beta beta square, 1 beta square beta and 1 1 1, I a, I b, I c, these are known to us. Therefore, I a 1, I a 2, I a 0 is equal to 1/3, 1 beta beta square is the same matrix, then I a is equal to 0 and this is I b and this is I c, because that your this double line to ground fault that it has happened between phase B and C. So, I a is equal to 0. So, here if you put I a is equal to 0, then it is I b I c. Therefore, I a 0 is equal to, from this equation, because I a 0 is equal to 1/3 then your I b plus I c. That means, I b plus I c is equal to 3 I a 0. Therefore, this one I b plus I c is replaced by 3 I 0. That is why V b is equal to V c is equal to 3 Z f I a 0. Now, the symmetrical components of voltages are given by, these are again known to us. So, V a 1, V a 2, V a 0 is equal to 1/3, 1 beta beta square, 1 beta square beta, 1 1 1, and this is your V a, V b and V c is equal to V b. Here we are writing V c is equal to V b, this is equation say 32. Now, from equation 32 you can write directly I am writing, if you write V a 1 for example, if you write V a 1, it will be V a plus beta V b plus beta square V b again, because V c is equal to V b. If you write V a 2, that is also 1/3, you will write V a plus beta square V b plus beta V b, that means beta square plus beta, both the equation is common. That means, directly we can write that V a 1 is equal to V a 2 is equal to 1/3 in bracket V a plus beta square V b, this is equation 33. So, and the V a 0, the last one, it is V a plus V b plus V c is equal to V b, that means V a 0 is equal to 1/3 V a plus 2 V b. So, this is equation 34. So, using equation 33 and 34, that means using these two equation, that means you subtract equation 33 from equation 34. If you subtract you will get we want V a 0 minus V a 1, we want V a 0 minus V a 1. So, subtract equation your 33 from equation 34. If you do so, V a 0 minus V a 1 will come like this, 1/3 2 minus beta square into V b. Now, V a 0 minus V a 0 1/3, add 1, subtract 1, if you add 1, 2 plus 1 3, then minus you take common, it will be 1 plus beta square into your V b. So, in this case, in this case we know that this identity 1 plus beta square is equal to 0. During symmetrical component we have given this. So, put here it is 0, that means V a 0 minus V a 1 is equal to 3, because of this 3 into 1/3 V b, that means V a 0 minus V a 1 actually is equal to V b. So, and V b is equal to V c. So, naturally it will be equal to V c. So, V a 0 minus V a 1 is equal to 3 Z f I a 0, because V b is equal to 3 Z f I a 0. Here we have in equation 31 we have shown that V b is equal to V c is equal to 3 Z f I a 0. All exercise has been done for you on the right hand side. So, in this case, that means your V a 0 is equal to V a 1 plus 3 Z f into I a 0. This is actually equation 35. That means, equation 33, that means this equation, the equation 33, 35 and 30, these three equations we can draw the connection of the sequence network as shown in figure 6. So, 33, 35 and 30. So, equation 33, it is actually V a 1 is equal to V a 2, This is the first thing. Then equation 35 I have written right hand side, it is VA0 is equal to VA1 plus 3 ZF IA0, and equation 30 actually I am rewriting this equation just for drawing this diagram, and it is given IA1 plus IA2 plus IA0 is equal to 0. That means, these 3 equations, suppose these, for example, suppose these 3 equations are given to you and you please draw the complete your sequence network connection. Suppose some fault has happened, these equations are given to you. For example, say after solving somebody has given that these are the positive, negative and 0 sequence relation, you please make the circuit. So, 33 VA1 is equal to VA2, that means it suggests that positive and negative your sequence it has to be connected in parallel. And another is IA1 plus IA2 plus IA0 is equal to 0, this condition also you have to satisfy, and VA0 is equal to also you have to satisfy VA1 plus 3 ZF your IA0. How one will make it? So, the black color is my positive sequence network, EA is there, Z1 IA1, this one is my negative sequence one, this is Z2, again by there is a black ink I have used, right, and this is 0 sequence Z0. Now, first thing is that my VA1 is equal to VA2, and all this connect IA1 plus IA2 plus your IA0 is equal to 0. So, in this case what you will do, that this your VA0, this your 0 sequence, this negative sequence network, this is IA2 is coming here, and from 0 sequence this IA0 is coming here, and from positive sequence IA in coming onwards you have to make a junction point such that IA1 plus IA2 plus IA is equal 0 is equal to 0. So, that means this IA1 is coming here, IA2 is coming here, IA0 also coming here. At this point you apply Kirchhoff's first law. So, IA1 plus IA2 plus IA0 is equal to 0. Similarly, this is your plus connection, right. Similarly, here also that you have to see first outgoing, and here also as you have connected here means here also you have to connect, but question is that VA0 is equal to VA1 plus 3 ZF IA0. That means, this IA0 is this current is flowing to the fault impedance, total is coming as equivalent 3 ZF. That means, this is the IA0 current is entering going like this. So, this is IA0. So, leaving this terminal, but it will be 3 ZF IA0 will be there, because VA0 is equal to VA1 plus 3 ZF. So, 3 ZF will come here, and here also IA2, this is the current path for IA2. So, from this IA2 also will leave, and this is the current path for IA1, it will also leave, but this 3 ZF will come. If ZF is equal to 0, then it will be same as before, only one is incoming, and here it is all currents are outgoing. So, if you, and this is your what you call, this is VA1 is equal to VA2, because if you make a KVL here, look, this loop will go like this, it will go like this, this is your plus VA2, it will come like this, minus VA1 is equal to 0, only it will go like this, it will go like this, go like this, it will go like this, it will go like this. So, that is why VA1 is equal to VA2, and if you make that VA0 is equal to VA1 plus 3 ZF your IA0, then in this case if you make loop like this KVL, you come here, right. So, it will be your plus your VA0 plus VA0, then this current is going, so opposing. So, minus IA0 into 3 ZF, and then your minus VA1 is equal to 0. That means, VA0 will be equal to VA1 plus 3 ZF IA0, and at this point or at this point IA1 plus IA2 plus IA0 is equal to 0. So, this is the equivalent circuit connection for your what you call that your double line to ground fault. So, from your here from your intuition only you have to make the circuit connection correct. So, from this condition different type of faults will be there. So, accordingly you have to make it, suppose all the conditions you have to make, and accordingly you have to this thing different places different way this diagram is given, but I prefer always this way, make positive negative 0, after that look into the equation and accordingly you try to make it. So, therefore, this is the sequence network connection for double line to ground fault. I hope this much you have understood. Now, this circuit if you make equivalent, equivalent is there. Suppose this is for you only, I have made it figure 6a, this is figure 6, this is EA and this is Z1. So, this current is going I1. Now, this is Z2, the current is going here, because all the summation of all this current is 0. So, this is Z2 and this is your, and this is IA0 and this is Z0 and 3ZF, they are in series. So, Z0 3ZF, this current is there, that means your these two are in parallel, that your what you call that negative sequence and 0 sequence, but here Z0 plus 3ZF, these two are in parallel. It suggests also that VA0 is equal to your this thing, what you this thing, what you call that this positive, sorry, this negative sequence and this 0 sequence, these two are in parallel. So, that means and from here these two are in parallel. So, their equivalent will be Z2 into Z0 plus 3ZF divided by Z2 plus Z0 plus 3ZF. So, that means your this equation also I have written, that is why that VA0 is equal to VA2 plus 3ZF IA0. This is because earlier we have made it that VA1 is equal to your VA1 is equal to VA2. This one we have made it. That is why that means VA0 instead of V1 we can write also VA2 plus 3ZF IA0. That means this suggests that your negative sequence and your 0 sequence right, they are in parallel, but their fault impedance will be there. If ZF is 0, then 3ZF term will not be there. So, here they are referring to your this one, referring to your equation 33. So, that means my IA1 is equal to your EA divided by this Z1 plus the parallel combination of this Z2 into Z0 plus 3ZF divided by Z2 plus Z0 plus 3ZF. This is equation 36. Similarly, if you apply KVL in this loop, this circuit is the simplest version of this one, right, equivalent version of this one, same circuit, but drawn. If you apply KVL in this loop, so it will be Z1 IA1 minus your Z2 IA2 minus EA is equal to 0. That means, I am writing this from this circuit only here, for such that you can understand easily. That means, your Z1 IA1 minus Z2 IA2 minus EA is equal to 0. That means, from upon simplification IA2 is equal to minus in bracket EA minus Z1 IA1 by Z2. This is equation 37. Similarly, in this circuit again, here in this you make this, that means KVL, this second one, the Z1 IA1, right, minus IA0 in bracket into Z0 plus 3ZF minus EA is equal to 0. If you do so, then same I am writing Z1 IA1 minus Z0 plus 3ZF into IA0 minus EA is equal to 0. That means, upon simplification IA0 will be minus in bracket EA minus Z1 IA1 divided by Z0 plus 3ZF. This is equation 38. So, this way one has to solve, when data will be given and how things can be solved, that through numericals we will see, but only before moving to that I would like to tell that particularly the positive sequence, negative sequence and 0 sequence component, when you consider for a problem and fault has occurred, these problems are little bit of I will say that little bit of complexity is involved, a little bit of long, I mean lengthy, but we will take few examples and we will show you how things can be solved. So, that means, so far we have studied line to line fault, line to ground fault and your what to call double line to ground fault and all the expression. I hope you have understood this, but only different fault is, I mean some different type of fault is created. So, you have to generate those equations, you have to and accordingly you have to draw the sequence network. Next is that open conductor fault. These are although very rare, but suppose a open conductor, broken conductor. Open conductor means broken conductor. Suppose this is the figure 7, you have a phase A, B, C, current flowing through these are IA, IB, IC, but suddenly in phase A, suppose conductor is open. So, what we are doing is we are marking A, F dash, then B, B dash and C, C dash, right. So, one conductor is open, that is phase A conductor is open. So, in that case, as this is a continuous, this is a there is no broken part here, there will B and B dash point is common, C and C dash point common, that means B your V B B dash is equal to V C C dash is equal to 0. This is equation 39, because B and B dash actually common point, C C dash common point. So, no broken part here in phase B and C. So, V dash B B is equal to V dash C C is equal to 0. This is equation 39. And as this phase A conductor is broken, so I A is equal to 0. So, I A is equal to 0. These are the boundary conditions. Now, this one if you put in symmetrical component, we can write like this in terms of this equation is always known to you. We can write down V A dash 1 positive sequence, V, that is open conductor cases, then V A dash 2, then V A dash 0 positive negative 0 sequence component is equal to 1/3, because we are taking the voltage V A dash is equal to V A dash 1 plus V A dash 2 plus V A dash 0, right. So, that means it is equal to 1/3 1 beta beta square 1 beta square beta 1 1, these are known to you, into V A dash V B B dash V C C dash. The way we are doing now, V A 1 V A 2 V A 0 is equal to this matrix into V A V B V C. Here also, because of open conductor, that V A dash V B B dash V C dash C C dash, but V B B dash and V C C dash is both are 0, here 0, because of this one V B dash, these two are 0 from equation 39. Therefore, we can write this is 0 0, we can write then V A dash 1 is equal to V A dash 2 is equal to V A dash 0 is equal to 1/3 V A dash. This is equation 41. The reason is very simple, V A dash 1 is equal to 1/3 V A dash, V A dash 2 is equal to 1/3 again V A dash, and V A dash 0 is equal to 1/3 again V A dash, because these two are 0. So, these all are equal, suggest it is a parallel connection, and I A 1 plus I A 2 plus I A 0 is equal to 0, because phase conductor A has broken or open, that means I A is equal to 0. I A is equal to 0 means your I A 1 plus I A 2 plus I A 0 is equal to 0. This equation from this you have to draw that means this equation 41, this is equation 41 and 42. This equation, these two suggest a parallel connection of sequence network as shown in figure 8, that means next figure. That means they are connected parallel, and sum of this current positive, negative and 0 sequence is 0. That means this is your say I make it because the conductor open conductor only. So, this is suppose A F dash A F dash A F dash, right. This is for phase A. Why you are making A F dash? Because phase A conductor has open positive, negative and 0 sequence, that is why A F dash, that is why it is your F dash. Your I mean, if you want you can make a line like this, that conductor open F dash and here also, right. So, in that case this F dash for positive sequence, negative sequence, 0 sequence, all they are in all parallel, because all voltages are same, right, and all the sum, and from here current is I A 1, from here current is I A 2, from here current is I A 0, because I is equal to 0. So, at this there is a meeting point. So, I A 1 plus I A 2 plus I A 0 is equal to 0, cause of first law, and this is the sequence network for one conductor open. So, things are very simple, only from that from that fault condition you have to write those equations, boundary conditions, and then you can mathematically you can manipulate, and you can easily construct the positive, negative and 0 sequence connection. Then one more, the two conductors open. Suppose phase A, phase B and phase C, both conductors are open. So, it is A dash, then B B dash and C C dash, but phase B and phase C conductors are open. That means, I B is equal to 0, I C is equal to 0, right, and this is a continuous your V A dash, it will be 0, because there is no broken path here, A and A dash common point. So, V A dash is equal to 0, and I B is equal to 0, I B is equal to 0. These are actually boundary condition. So, with this with this, so from from this figure boundary condition, we can write that V A dash is equal to 0, I B is equal to I C is equal to 0. So, in terms of symmetrical component, you that V A dash is equal to 0 means V A dash 1 plus V A dash 2 plus V A dash is equal to 0, 40. This is positive, negative and 0 sequence component, and I B is equal to I C is equal to 0. And if you same way, if you go for symmetrical component, I am not putting it here. Now you have understood. Now you have understood everything. You will get IA1 is equal to IA2 is equal to IA0 is equal to 1/3. That is all IA1, IA2, IA0 is equal to 1/3 IA. All are same. That means this condition suggests actually a series connection, because IA1 is equal to IA2 is equal to I0. When currents are same, it is suggests a series connection. So, if it is a series connection, this is your F dash, F dash, F dash. I have told you earlier also. Series connection means this is your positive, positive to negative, then positive to negative, then positive to negative, and this is your positive sequence, this is your negative sequence, and this is your 0 sequence correction. So, it is IA1, IA2 is equal to IA1, IA0 is equal to IA1, because all are same, that is 1/3 IA. This is equation 46. So, this is actually sequence network for two conductors open. So, although these are very rare phenomena, right, these are very rare phenomena, and but for the sake of completeness, I took this one. And even simultaneous occurrence of, I told you, suppose line to ground fault, at the same time double line to line fault, very rare, but we will see. I think we have taken one problem later on, that we will see. Now, what we will do that this example actually we have taken from your previous symmetrical component, because then it will be easy for you to understand, right. This example actually is the same example 4 of that your symmetrical component, details have been given there. This is the same problem is taken, and same diagram, and that same diagram, right, same diagram, everything, all data are also same, all the data are available in that in this problem, all the data, or whatever data we have made it. For example, 4 of symmetrical component, I have taken the same data, all data are same, such that it will save time, it will help us to understand this. So, the same problem, same diagram we have taken. So, all data remain same of example 4 of the symmetrical component, and there is a fault at point G, that is solid line to ground fault. When it is telling solid line to ground fault, means that fault impedance is 0, and we have to find out that current supplied by the generator, by the motor, and how things will happen. So, all the parameters are same. Now, when you will see the data, of this problem, but still I have brought that previous one, that motor terminal voltage was 10 kV. Now, fault actually has happened to the motor side, this motor side, and that is why here it is written data same as example 4 of the previous topic, that is symmetrical component. You have all the data. Now, if it is so, and fault has occurred here, fault has occurred at point G. Now, if it is so, first I will show you the diagram, then the connection. So, this positive, just hold on, this positive, negative and 0 sequence diagram for this network was shown to you earlier. This is your positive sequence one. Earlier I told you how to make it, with all the voltage sources, everything will be there, positive and all the positive sequence impedance. Negative sequence parameters are same, but only there is no voltage source, and all the 0 sequence also, this has been shown, that how it has been drawn has been explained in detail. So, same network and same diagram. Now, there is a point that fault has occurred. I mean, there is a point here, that is your near motor terminal, this time there is a point here. Suppose this is your G, that means in this diagram, that is P, Q and G things are there. So, in this diagram, that is there is a point at G, this is G, at this point a fault has occurred. So, in this case, that this is the point G, say that fault has occurred, line to ground fault, solid line to ground fault has occurred. So, in this case what will happen, that fault, this is your, then how to connect. Now, that this is your same positive sequence network of example 4, same negative, same 0 sequence. So, in this the fault has occurred here, this is reference bus, this is reference bus, this is reference bus. So, fault has occurred here. So, make this ground to the reference bus of that your negative sequence network, and here also ground to reference network, and then here also this is your G point, rather G point to reference network, and this is G point, and it will go to the your reference bus. So, this point is a G, that means in this your what you call this point is G, the fault has occurred here, line to ground fault has occurred here. So, that means this is my point G, they connected to the reference bus, then G connected to the reference bus, and this is also G connected to the reference bus. Before solving this problem, that when you will solve it, using for 3 phase fault, we have made that pre-fault voltage taken out and equivalent Thevenin representation. 3 phase fault, only our objective was to see that your Z bus building algorithm, although little bit complicated and some few problems for solving this, but more emphasis we have given here the symmetrical component and unbalanced fault. So, in this case, if you look at that you have to find out your what is the pre-fault voltage, because motor side fault has occurred. So, its voltage was 10 kV, that we will see later. Now, question is that if you look into that, the 0 sequence network, same network, right, that your 0 sequence current actually will flow from the motor side, because this is your there are 2 motors, one is your what you call ungrounded, and another this one is your what you call, this is the better this one. If you take this one, this is star connected, this is star connected, and this is through some impedance, it is grounded. So, here also I have missed that it is star connected, but ungrounded. So, here that means this 0 sequence diagram, that it is connected to the reference. If you see, the circuit is completed, but if you look at the generator side, right, because of the isolation, star is grounded, but delta is here. So, there is an isolation. So, that means from the generator side there will be no 0 sequence current, but from the motor side there will be your what you call, there will be 0 sequence current, right. So, that means your later that means when you will solve this, that means all the 0 sequence current by whatever it is, it will flow from the motor side, because you see it is getting a path, it is getting a path, it is getting a path like this, but this side there is isolation. So, no current will flow from the generator side. This you have to judge looking at the 0 sequence network. That means if you make only the your Thevenin equivalent from the for the positive sequence network. So, motor side voltage was 10 kV. So, pre-fault currents are your pre-fault currents are neglected. So, we can say Eg double dash is equal to em1 double dash is equal to em2 double dash is equal to Vf0 is equal to 10 by 11.909 per unit, but motor side terminal voltage 10 kV, base kV you have taken 11. So, 0.909. So, this is my your Vf0 this thing, and next is this all these things, sum up these two and take the equivalent of this parallel 0.345 and 0.69 j, take this equivalent, its equivalent will be actually j 0.23, and this side is j 0.20, j 0.49, we have to add these two and take the equivalent. If you take, then Z1 will become j 0.172 per unit, and Z2 is equal to Z1 will be j 0.172 per unit, and Z0 is equal to j 3.264, this is the j 3.2. This all these parameters have been computed for example 4 in symmetrical component. So, all parameters we are taking, other this one will not be required for that kind of fault, while fault had occurred at your what you call point G. So, that means, and this is the Thevenin equivalent. Now, that means similarly this one also, these two you add and these are there, make equivalent parallel, and this one in this case only j 3.264 will come. So, if you make that equivalent circuit, so this equivalent is coming your Z2 is equal to Z1 is equal to this one and this is this one. So, equivalent circuit will be equivalent circuit will be this one. This is reference bus, this is J.172, J.172 and J3.264 and IA1 is equal to IA2 is equal to IA0. So, in that case I1 will get Vf0 upon Z1 plus Z2 plus Z0. So, substitute all this. If you substitute all this, then you will get IA1 is equal to minus J 0.252 per unit and IA1 is equal to IA2 is equal to all are same, right. I have not shown here, but this is IA1, this is IA2, this is IA0 series circuit, all are same. That means your this will be minus J 0.252. Now, fault current will be 3 IA0, that is your 3 into minus J your 0.252, right. So, that means it is minus J 0. Ultimately is coming 75 your 6 per unit. So, this way this what you call this way you have to solve that 0 sequence, your positive sequence, negative sequence and 0 sequence you have to understand, and then only you can apply that how and where fault has occurred, and accordingly you have to see that how all parameters are computed correctly, and then you can easily solve that what will be my fault current. So, thank you, again we will be back.